In this chapter, we lay the groundwork for the estimation techniques and hypothesis testing procedures that will be developed in later chapters. We move from discussing the likelihood that a particular subject will have a score in a specific range to the more important question of the likelihood that a sample mean or a sample proportion will fall within a specific range. This chapter is about describing graphs of sample means and sample proportions, and these graphs are referred to as sampling distributions. Just before the presidential election in October of 2004, when the incumbent President Bush was challenged by Senator Kerry from Massachusetts, two different polls were conducted. The Gallup poll estimated the percent favoring Kerry to be 49%, making it a very close election, whereas the Rasmussen poll estimated the percent favoring Kerry to be only 45.9%, not such a close race. So why do polls vary? The answer is simple: because the subjects are different. Different people yield different results. So returning to the presidential election of 2004, imagine conducting 2,000 separate polls, each consisting of 1,000 voters. For each of these 2,000 polls, you record the percent favoring Senator Kerry. What would that graph of 2,000 sample proportions look like? Well, it would look something like this. It has a familiar bell shaped, with most of the samples reporting a proportion of about 48%. There are a few samples that reported only 42 or 43% favoring Senator Kerry, and a few reporting as much as 52 or 53% favoring Senator Kerry. Essentially, all of the proportions fell in the range from 42 to 53%. So we suspect the graph of sample proportions may be normal, and in fact it is. We can visually estimate the mean to be about 0.48. In fact, since the graph is normally distributed, we could estimate the standard deviation. The range of the data is about a 0.10, and this corresponds to 6 standard deviations, 3 above the mean and 3 below the mean. Now, if we do the math, 0.10 divided by 6 is 0.0167. So a very rough estimate of the standard deviation is 0.0167 or 1.67%. One other detail I'd like to point out is that the horizontal axis is labeled sample p-values and p-hat. P-hat is the symbol for a single sample proportion, and what we have is a graph of 2,000 sample proportions. The truth is, we do not have to estimate the standard deviation of this distribution of sample proportions. If we know or can accurately estimate the population proportion P, then there is a well-known formula for finding the standard deviation. It is the square root of P times Q divided by N, where Q is 1 minus P, or in this case, the proportion who do not plan to vote for Senator Kerry. So here is a picture of what the sample proportions look like. It is centered at P, the true proportion, and if we go 3 standard deviations on either side of this center, we capture 99.7% of the sample proportions. The picture we just described has a fancy name. It is called the sampling distribution of a proportion. It displays all the values a sample proportion could assume for all possible samples of a given size. To see the practical reality of this, Senator Kerry received 49% of the popular vote when the votes were counted for the 2004 presidential election. So, in fact, the mean of the sampling distribution of proportions is really 0.49, and the standard deviation as calculated from the formula is 0.0158. You may remember our rough estimate was a 0.0167, which wasn't bad. Taking this one step further, if we consider an interval that is 2 standard deviations from the mean of 0.49, by computing 0.49 minus 2 times 0.0158 and 0.49 plus 2 times 0.0158, we can announce that 95% of all samples of size 1,000 voters will produce a sample proportion favoring Kerry of between 45.8% and 55.2%. This election was clearly too close to call. This slide says it all. If the sample size is relatively large, sample proportions are normally distributed with a mean equal to the population proportion and a standard deviation equal to the square root of P times Q over N. Since sample proportions are normally distributed, calculating z-scores will be the secret to answering questions about sample proportions. And since the issue of making generalizations about sample proportions is a big one, I suggest you remember this important z-score formula. This is too easy. There must be a catch. And there is one. The previous slide said provided the sample size is large enough. What does that mean? Well, there is an official rule. The sample size n has to be large enough so that both n times p, which is referred to as the number of successes, in our example the number who plan to vote for Kerry, and n times q, which is referred to as the number of failures, which in our example is the number of people who do not plan to vote for Kerry. Both of these must be at least 10. The sample size in our example was 1,000, and the computation of n times p and n times q yields numbers much bigger than 10. So sample proportions based on samples of size 1,000 are normally distributed in this example.